Today we're talking about a new topic called the solubility product constant. What we're going to do today that's a little bit different is we're going to look at solubility equilibria. So we're going to look at compounds that do not dissolve very well in water and what their equilibrium concentrations are like, and we're going to do some calculations based on that. So to start us off, let's get that. I gave you the definition of a solubility equilibrium earlier on in the unit, but we'll just sort of recap that. A solubility equilibria is basically when a reaction involves dissolving or forming a solid from a solution. So here's an example of an equation that you probably would have seen in grade 11. It's a double displacement reaction. Silver nitrate and hydrochloric acid makes silver chloride and nitric acid. And you'll notice that you could have checked on your solubility chart to determine that your silver chloride was actually a solid and it wouldn't dissolve in water. If we rewrote this and eliminated your spectator ions, our net ionic equation would be your silver ions plus your chloride ions give you your solid silver precipitate. Here's what's actually happening in the beaker if you were to actually do this reaction. Oh, let's see if this works. Yes, okay. So here is an Erlenmeyer flask of water, and I think some of the volume here might be loud, so I apologize for that. I wonder if I can control it. Nope. So when silver chloride actually dissolves in water, we know it doesn't dissolve very well in water. So what's going to happen is some of the ions are actually going to break apart from the solid and float around. But most of them aren't, and that's why it's insoluble in water, and we write it in the equation as a solid. But as you can see, as we're sort of going through this, the equilibrium is established because as some ions float off, ions that are already floating will sort of attach back onto the solid. So this is how the equilibrium occurs. So you have some solid dissolving and some dissolved solid, or dissolved ions are reforming into a solid. So that balance of making ions and making solid keeps happening over and over and over again. So that's what's actually happening. So it is still solid technically because not all the ions will dissolve in water, not all the ions will separate. But there are a couple of ions that will separate, and so we can calculate the concentrations of those ions. So there's, again, our net ionic equation. And because, again, we know it's reversible, it doesn't matter which way we write it, if we write it with the products or the solid on the reactant side or the product side. So that's a little bit how it works, and that's what we're going to be looking at in a little bit more detail today. So now when we look at the solubility product constant, this is basically your K value for solubility. So we've been calculating KEQ up to now. So now we're basically still calculating KEQ, but now we're just going to call it something different. We're going to call it KSP because we're dealing with a solubility. So that's why we call it KSP, which is your solubility product constant. So for a partly soluble or insoluble solid such as silver chloride, here is again your equilibrium expression. So you have some solid and it'll dissolve into your ions, and then those ions reform into solid, and that reaction is completely reversible. So how do we write our expression for KSP? It's basically the exact same as for KEQ, except we're not going to include a concentration for a solid because we've already established that there is no concentration when you have a solid. A solid can only be measured with mass. So your KSP equation ends up in this case being your concentration of your silver ions times your concentration of your chloride ions. Okay, you're not going to divide by anything from your reactants because, again, your reactants are solid, so we're just not going to write anything in. So there's your KSP equation. Okay. If you end up with coefficients in your balanced chemical equation, so let's say there was a 2 there, you'd have to make sure that they, again, become exponents. So I would put a 2 there. Now in this case, obviously that's incorrect, but at least you know to follow those same rules as we did when we were writing our expressions for KEQ. Oh, so there we go. So let's see if you can write the expression for the solubility product constant of all three of these. So again, these should be pretty easy for you because it's exactly the same as KEQ, but we're just calling it KSP because it's dealing with the solubility of a solid. So see if you can write those out. If you want to pause the video, I'm going to do the answers now. So for the first one, so for iron 3 hydroxide, again, it would be your products over your reactants, but we don't count the reactants in this case because it's a solid. So it ends up being your iron ions times the concentration of your hydroxide ions, and we have to put the 3 as the exponent there. For silver chloride, again, it would be your silver ions squared times your sulfide ions, concentration of the sulfide ions. And then for the last one, calcium ions to the third, and your phosphate ions, 3 minus squared. So I haven't really taught you anything new other than the fact that we're dealing with solids now that don't dissolve well in water. All right, so let's actually do an example where we calculate the KSP. So we're calculating the solubility product constant. So it says here, a scientist prepares a saturated solution of lead iodide. Independent measurements show that the concentration of lead in this solution, so your lead ion, is 1.3 times 10 to the negative 3 molar. Calculate KSP. So first thing you need to do is you need to come up with your equilibrium expression. So in this case, for lead iodide, we'll use PbI2. That's your solid. And we know it's going to, some of it will dissolve into its ions, but not a lot of it. So you'll get Pb2 plus and 2I minus. Now, if we just continue to sort of write what was in the question, I gave you the concentration of your lead, which was 1.3 times 10 to the negative 3 molar. Okay, but you don't know your concentration of I. And the other thing you need to do is calculate your KSP. So your expression for KSP, you should be all able to write that now. So it's your concentration of lead ions times your concentration of iodide ions squared. So we know this, we can plug that in. We just have to figure out what your concentration of iodide ions is. And then we can plug those two numbers in and calculate our KSP. So how do we find out what's the concentration of your iodide ions? If you want, you can fill in a nice chart, but a lot of you might see, based on your balanced chemical equation, your iodine is, you have 2 iodide ions for every 1 lead iodide that basically breaks apart. So if I've broken apart the lead iodide into lead, and this is my concentration, this is going to be 2 times my lead concentration, because again I have 2 iodide ions here for every 1 molecule of lead that breaks apart. So I'll just rewrite that so we can see that a bit better. PbI2 as a solid. So I know it's going to be twice as much as my lead concentration. So it'll be, 2.6 times 10 to the negative 3 molar. So now I've got my 2 concentrations, I'm going to plug them into my equation. So my lead concentration is 1.3. My lead concentration is 1.3 times 10 to the negative 3 molar. And I'm going to times that by 2.6 times 10 to the negative 3 molar squared. So when I do all that, my final answer ends up being around 8.8 times 10 to the negative 9. So there's my KSP for this reaction. All right, let's do another example now. So now we're going to do the reverse. I'm going to give you the KSP, and I want you to calculate the solubility, or the concentration. So this is the solubility calculation, because I'm giving you the KSP. So KSP for Ag2S, silver sulfide, is 1.6 times 10 to the negative 49. Very, very low. Calculate the solubility in moles per liter. So again, before you start anything, write out your equilibrium expression for this. So I've got Ag2S, that's a solid, and we know it's going to break apart into 2 silver ions and 1 sulfide ion. Again, you can set up an ice chart for this if you'd like. It might help you. So I'll show you how to do that in this. You could have done it on the last example too. I'll show you how to do it for this. So in your ice chart, your initial concentration of Ag2S before anything happened doesn't exist. You don't have a concentration. The change is not going to, it's not going to change by anything concentration-wise, and your equilibrium, you're not going to get a concentration ever for the solid. So really the only thing we're looking at are the two ions. So initially, before you dropped this in water, the concentrations of both of these ions were 0. How are they going to change? Well, after some of it dissolves, this one's going to go up by 2x, and this one's going to go up by x. So at equilibrium, you have 2x and x. If I plug that into my KSP equation now, I know my KSP equation is my Ag concentration squared times my sulfide concentration. So if I punch in those numbers now, I have 2x for my Ag concentration, then I square it, and I have x for my sulfide. So I basically just brought those two numbers down here. And I know that that equals 1.6 times 10 to the negative 49. So now all you have to do is solve for x. 1.6 times 10 to the negative 49 equals 4x cubed. So again, you guys should be able to figure that out on your calculator. You divide both sides by 4 and take the cubed root of it. You should get that x equals 3.4 times 10 to the negative 17. So that gives you your final concentration of your sulfide ions. If you multiplied that by 2, it would give you the concentration of your silver ions. But if I'm looking at the solubility for my initial product, or my initial sort of reactant, my initial solid there, that's what I'm looking for the solubility of. I know that this is in a 1-to-1 ratio with my sulfide ions, and I know that my sulfide ions are what I just calculated. So my solubility, shouldn't put concentration, we'll do my solubility of Ag2S ends up equaling the concentration of my sulfide ions. So that means it's, again, the same number, 3.4 times 10 to the negative 17. All right, so those are your two sort of basic calculations. We're going to go through a couple of more, and then we might have to finish up with some more in class, but we'll see how many we can get through on this video. So the next thing we're going to look at is solubility and what's called the common ion effect. This is new for you, so pay attention. The common ion effect means that there is a decrease in solubility, which occurs when an ionic compound is dissolved in a solution that contains an ion in common with the solid. So it's basically consistent with the principle of Le Chatelier. So if I have this reaction, silver chloride gives you silver and chloride ions. If I add NaCl to this, what's the common ion in both cases? The common ion would be chlorine, right? So because of that, if I add sodium chloride to this system, that means I'm adding chlorine. I'm adding this. So what does that mean? That's my common ion, so the common ion effect. If I add that, I'm going to create more product, right? I'm going to shift that way. And that in effect decreases the solubility of AgCl because now I'm making more solid, so less of it will dissolve in water. That means my solubility is decreased. So again, if I add NaCl, I'm essentially adding the chloride ions to the equation, which shifts my equilibrium towards the reactant side. Because of that, now I'm making more reactants, I'm making more solid, and I have less of these two ions dissolving, which means I have decreased the solubility. All right, so let's do an example of a calculation with the common ion effect. So it's asking you here, what is the solubility of a barium sulfate solution, a barium sulfate in a solution that already contains 0.25 molar of sodium sulfate? The KSP of barium sulfate is 8.7 times 10 to the negative 11. So here's what you have to realize. When you're doing the common ion effect, usually one of your solids is aqueous when it's dissolved in water, okay? So it's not a solid. So Na2SO4, when it dissolves, I'll write this down here at the bottom, Na2SO4, when you put that in water, it will completely dissolve into sodium ions and sulfate ions. Okay, so if I start off with 0.250 molars of that, it means I end up with 0.250 molar of my sulfate ions and double, so 0.500 molar of sodium. So I've got this solution in a beaker of Na2SO4. And I know my concentrations of the ions because it is soluble in water. So I've just calculated those out. Now what I'm going to do is I'm going to add barium sulfate to it. So the question is, what is the solubility of that barium sulfate, or how much of it will actually dissolve, given that I already have some sulfate ions present in my solution? So that's what we're trying to find. So I'll leave that little diagram up. But if you start to fill in your ice chart now, I'm adding BaSO4 and I'm asking you for the solubility of BaSO4. So that's the ion that, or those are the ions that I'm going to focus on in my ice chart. So again, barium sulfate is solid, so I don't have a change in concentration or an equilibrium concentration for my barium sulfate. My barium ions, initially in my beaker before I added anything, I had 0 barium ions, but I had 0.250 moles of sulfate ions from the Na2SO4. So obviously when I added BSO4, my equilibrium is going to shift that way. So I'm going to add some barium, and I'm going to add some sulfate. Okay, it's a 1-to-1 ratio, so I'm going to go up by X each time. So my final barium concentration is going to be X. My final sulfate concentration is going to be 0.250 plus X. So now I'm going to take those two values for X, and I'm going to calculate my concentrations or my solubility of barium sulfate. So now all I have to do is solve for X. The first thing I have to realize, though, is that we did this in class. I can use the 100 rule here. So again, my KSP for barium sulfate is very, very small. So if I use my 100 rule, I'm going to get a value that's greater than 100, which means I can't get rid of this first X here, okay? But I can get rid of this one because it's going to be so small that 0.25 minus 0.00000001 or whatever that value of X is going to be is still going to pretty much equal 0.250. So I'm going to eliminate that to make my reaction simpler so that I don't have a quadratic equation. So now I can solve for X. So I know my KSP for barium sulfate is going to be my concentration of barium ions times my concentration of sulfate ions. And I gave you the KSP value of 8.7 times 10 to the negative 11. So that's going to be, my barium was X, and my sulfate was, 0.250 minus X. But again, we dropped that because X is going to be so small. So we just did that. So now all I have to do is divide by 0.250, and I get the X is 3.48 times 10 to the negative 10, which is pretty small. Okay, that's the same as saying 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I look at that, I know my 100 rule worked. So check this out in red. So back here, this could have been 0.250 minus X. But check out my value of X. It's so small. So when I actually do the subtraction, it ends up pretty much being 0.250. 0.000000348, whatever. But it's so small that when I round and I use my significant figures, my answer is still 0.250. So that's why the 100 rule works, and that's why it was okay that I used it in this case. I've solved for x, and that's my solubility of barium sulfate. So if you want to write that in, BaSO4 is 3.48 times 10 to the negative 10 molar. All right. I want you guys to try this on your own. I'll give you the answers, but see if you can get it on your own. I'm going to save a little bit of time here. Calculate the solubility for the exact same solute, BaSO4, and water with no added SO4. So I've set up the ice chart for you. So instead of having 0.250 molars of SO4, now you have 0 SO4. So how would that have changed your solubility? Okay, so see if you can answer that. And you should get 9.33, this should be your answer, times 10 to the negative 6. So if you want to pause and figure that out, that's fine. Notice how my initial concentration with the common ion effect was much lower than my my solubility without that SO4 present. And that makes sense because if I add more of that, I'm shifting the equilibrium that way, which decreases the solubility, meaning that I have a lower solubility, an actual lower number over here. So I know I've done everything right, and that's sort of my way of making sense of everything. So if you didn't get the answer to that, if you didn't get 9.33 times 10 to the negative 6, let me know in class. We're going to do one more example, then we're done. And the last example we have to do is figuring out if a precipitate will form. So this is a very common question on a test. So if I mix two solutions together, you're going to basically be able to predict whether or not a precipitate forms based on the KSP values. So we're going to calculate Q, just like we did in the last video, and compare it to your KSP value to determine if a precipitate will form. If Q is less than KSP, remember we always draw our arrow from Q to K. If Q is smaller than KSP, you're not going to have any solid because, again, your equilibrium is going to shift towards your reactants. And the way we've written out our reactants are your ions, like Ag plus and Cl minus, which means that if that's the way it's shifting, we have no solid, which is on the other side of your equation. Sorry, I didn't mean to write that. If we're shifting towards the right, you're making products. My fault. Okay, which are still your ions, Ag plus and Cl minus. Okay. If we're shifting, if Q is greater than K, you're going to shift back that way. Now you're basically going to form reactants. And the way we write out our equilibrium expressions, your reactants end up being your solid. So if Q is greater than K, your equilibrium shifts towards the left, and you're actually going to form that solid because that's what's on your reactant side. So let's do an example of that. You have some Na2CO3 and some calcium nitrate that are going to be mixed together. Will a precipitate form? So if we write out the double displacement reaction for this using the solubility rules, the likely precipitate is calcium carbonate. So if I had Na2CO3 plus CaNO3, if we look back to grade 11, I'm going to get CaCO3 plus NaNO3. So I have two of those, and I'm balanced. So your CaCO3 is going to be, if you make a solid, that's what your solid's going to be. So from the table in the back of the book, which is actually pretty cool, in the back of your textbook, you've got a bunch of KSP values for all of these solids that don't dissolve in water. We can actually look up the KSP. So if I don't give it to you, you can look it up in the back of the textbook. And the KSP is 8.7 times 10 to the negative 9. So that's your KSP for calcium carbonate, which is your Ca2 plus ions times your CO3 2 minus ions. And that equals 8.7 times 10 to the negative 9. So calculate the ion concentrations after mixing, and then calculate Q. So after we mix, this is the only tricky part because you got to incorporate a little bit of grade 11 in here. So after the ions are mixed, we have to calculate the concentration using C equals N over V. Okay, and in this case, your moles or your sodium carbonate will be, you start off with, you start off with 0.050 moles per liter of your sodium carbonate, and you have, so that's your concentration, and you have 0.025 liters. Let me write this a little bit better. I'm going to take that equal sign. So there's your concentration and your volume, but your volume is going to change when you add another 25 mils of your other solution. So it's basically what's happening is you don't have 0.5 moles per liter anymore. You're going to end up with 0.25. And that's your NaCO3. Na2CO3, sorry. Okay, so how did I get that? Well, you don't really need to know. I mean, if you want to calculate, you can do C times V and calculate your concentration of your moles. You can do that. But you don't really need to. You just need to realize that you've doubled your volume. You've gone from 25 mils to 50 mils. So what's that going to do when this is doubled times 2? It means you have to basically divide by 2 because your volume's on the bottom. So I started off with 0.05 molar, and I divide by 2 to get 0.025 molar. My concentration of my calcium nitrate is basically going to be 0.0020 molar. Divide by 2, 0.0010 molar of calcium carbonate. So if you didn't get that, or sorry, calcium nitrate, if you didn't get that, come talk to me in class and I can take you through it in a little bit more detail. But those are your concentrations after you've mixed, okay? Because after you've mixed, the volume changed. You didn't have just 25 mils, now you had a total of 50 mils. So now we can calculate Q based on those initial concentrations. So my initial concentration of my carbonate ion is over here. I'm going to do that in red, so that's this value here. 0.025. And do the whole thing in red. There. Okay. And my initial concentration of my calcium ions, I'll do that in green. So times 0.001 molar. So when I do that, my value of Q is 2.5 times 10 to the negative 5. Plot my value on a number line from Q to K. So if this is 0, this is 1, say, my value for KSP is 8.7 times 10 to the negative 9, so really small. My value of Q only goes from 10 to the negative 5, so it's a little bit higher. If I draw my arrow from Q to K, and then I go back up here, from Q to K, I went in that direction. So what am I going to form? I'm going to form reactants, which means I'm making a solid. So in this case, for the answer, will a precipitate form? The answer is yes. So that's it. We're going to do some more examples in class and hopefully clear up any questions that you guys have.